Welcome back. Let's continue a little bit more on chapter 14. 2 to the second power minus 1 is 3. That's a prime. 2 to the third power minus 1 is 7. That's a prime. 2 to the fifth power minus 1 is 31. That's a prime. 2 to the seventh power minus 1, 127. That's also prime. These are all primes. Notice the powers are all primes here. These primes are called Mersenne primes. But if you continue, the next prime after 7 is 11. 2 to the 11 minus 1 is not a prime. So, are there any more primes? Mersenne primes? Well, search for Mersenne primes is an ongoing and a rich area of research. Okay? Distribution of primes. Here is an important, the prime number theorem. The ratio of the number of primes not exceeding x and x over natural log x. So number of primes not exceeding x, that number, and divided by x natural log x. The ratio of those two approaches 1 as x grows without bound. What does this mean? Well, first of all, this was proved in 1896 by Hadamard and Vallée-Poisson. What this means is the odds that a randomly selected positive integer less than n is prime are approximately n over natural log n over n. That is 1 over natural log n. Okay, so this talks basically about the probability of finding a prime. Here are some conjectures and theorems. A very beautiful conjecture by Paul Erdos. For every positive integer n greater than 2, there is an arithmetic progression of length n made up entirely of primes. Arithmetic progression means a progression, a sequence of numbers, each of which are separated from the previous one by a fixed number. For example, here is an example of an arithmetic progression. Let me say difference equals, I don't know, 8. And my starting number equals 4. I'm just making up some numbers, yeah? 8 is the difference, 4 is my starting number. 4 plus 8, 12. 12 plus 8, 20. 20 plus 8, 28. 28 plus 8, 36. Go on. This is an example of an arithmetic progression. That is, it's a sequence of numbers where the difference between consecutive numbers is the same distance. All right. Paul Erdős' conjecture is that for every integer n greater than 2, there is an arithmetic progression of length n made up entirely of primes. Okay. For example, here is n equals 3. So I want length 3 arithmetic progression. So 3, 5, 7. Look at the difference. Difference is 2. Here is another arithmetic progression. 3, 7, 11. The difference is precisely 4. 7, 13, 19. The difference is 6. 7, 19, 31. The difference is 12. So these are all arithmetic progressions of length 3. The difference is different. Okay, here the difference is 2, here the difference is 4, here it's 6, here it's 12. See whether you can find any more of length 3 made completely only of primes with fixed difference. It's not easy to do so. For n equals 4, 7 plus 12 is 19. 19 plus 12 is 31. 31 plus 12 is 43. This is it. If I add 12 more, I get 55, which is not prime. So for n equals 4, I was able to come up with only one sequence of length 4. For n equals 5, I have not managed to find any sequence. But the theorem is, well, this was Erdos' conjecture. For any n, you will be able to find arithmetic progression of that length. Turns out it's true. You can find. And it was proved in 2006 by Ben Green and Terence Tao, and the proof is very difficult. Okay? Here is another interesting problem. Consider the polynomial fn, n squared minus n plus 41. One can check f of 1, f of 2, that is, evaluate this polynomial when n is 1. You will get a prime number. Evaluate when n is 2, you will get a prime number. Evaluate when n is 3, you will get a prime number. Keep going. Even when you evaluate at 40, you get a prime number. But the moment you hit 41, you don't get a prime number. The question is there a polynomial such that fn is prime for every positive integer n? Well, the answer is no. For every polynomial, you will find a positive integer y such that fy is not a prime number. That's an interesting question too. Here is yet another conjecture, Goldbach's conjecture. It's very beautiful again. What does it say? Every even integer n greater than 2 is the sum of two primes. For example, let's take 4. 4 is an even integer. Is it a sum of two primes? Yes, 2 plus 2. What about 6? That's an even integer greater than 2. Is it a sum of two primes? Well, 3 plus 3. What about 8? Is 8 a sum of two primes? 3 plus 5. What about 10? It's 5 plus 5. What about 12? It is 5 plus 7. You see? What about 14? It is 7 plus 7. What about 16? 16 is, let's see, 11 plus 5. You see, I had to think a little more. The conjecture is that every even integer, can you always keep finding? Well, it has not been proved, but it has been checked to be true for all positive integers up to, imagine that, 1.6 times 10 to the 18. So a lot of work has gone into it. I'm sure computer time has gone into it, into checking until this, but there is no proof that it will always work. Okay? It's believed to be true. All right. Here is another beautiful conjecture. There are infinitely many primes of the form n squared plus 1, where n is a positive integer. This conjecture has not been proved. Okay? N squared plus 1, where n is a positive integer. A theorem by Henrik Ivanich states that there are infinitely many positive integers n such that n squared plus 1 is prime or product of at most two primes. So this is pretty close, but we don't know whether there are infinitely many primes of this type. Here is yet another